I think that then I'm going to get to radiation resistance and total power radiated. So first, I think these things are useful. You all remember I said, in general, an equal, you got it from potentials. Thank you. You got it from potentials, A and B, being actually minus the gradient of a voltage. And that's what electrostatics is, right? You assume all the charges are physically secure, and you get the voltage by taking, or you get the E field by taking minus the gradient of voltage, right? Now if you have charge acceleration or a current, and it's important that the charge is accelerating for the, well, I'll just leave it at this. This is generally true, and then I'm going to make I'm going to declare some things to you so you'll understand where the approximation comes in. This is equal to this minus, technically it's dA dt, where A is the magnetic vector potential, but we almost never work in the time domain unless it's a transient event we have to. Normally what you do is simply say it's equal to minus the gradient of the voltage minus, and it would be J omega A. Okay? I'm going to show you some things that are very, very useful. You'll see this in a second. So, in general, A, now you know what V is, but A was equal to the integral of mu 0 over 4 pi. This is for free space. We integrate over the length of the antenna, and it's going to be I, right, as a function of, say, position. I'm going to call it Z because most is in the Z direction. E to the minus J beta R. R would be the position of observation. It's going to be over the length, so we're going to assume it's in the DZ direction over R. Now that's just a general equation. If you have a field and you can get the differential A by just saying it's equal to I dL times e to the minus J beta R over R times mu 0 over 4 pi. This is just a constant. And what is mu 0 in terms of pi and forward thing? What is mu 0 on anybody? Isn't it 4 pi times 10 to the minus 7? How many know that? Well, 4 pi times 10 to the minus 7 over 4 pi is just 10 to the minus 7. All right, that's the first thing I'm going to mention. So this is really just 10 to the minus 7. Right here. Now beta, you can put down any equation you want. Beta is 2 pi over lambda. Beta is also equal to omega times square root of mu epsilon if you're in free space, right? So beta you can get any way you want. Now, the thing that's troubling you is when I do that integral, it's nice if it's a straight wire, it would be in dz, but what if it's not, if it's a loop? And that's what we're going to discuss today. But here's the real trick, all right? So first that constant. Next thing what you're going to find is, and put this down, in the far field, this is not in Whitworth's book, you can say E in general, and this is from wire antennas. From wire antennas, straight wire. Is just equal to minus J omega here times mu, or times really A in the Z direction times the sine of theta. Now, I'm going to show you what I mean, and it would be in the A theta direction, so you know. You're going to wonder, where did that come from? Please follow me on this, it's important. And this is something that, if I was sitting where you were, I would want to know this. So let's assume we have a short dipole for starters. We got this. We're going to assume the current's constant, it's I naught. Now, I'm going to be at an angle theta. I'm going to come out at distance r. And from last time, I know A in the Z direction. This is going to assume the total length here, L, is less than lambda over 10. So this is a critical feature. It's a short dipole. The length is from top to bottom And the current distribution, we're assuming, is just I naught. It's constant. We know better. We know at the ends it has to go to 0, but for now, it's useful to do this. Now, AZ is something I put down. DAZ was just mu 0 over 4 pi times I, call it I as a function of Z, dz times AZ e to the minus j beta r. But when you integrate over a length, if it's a short length, you just weigh that by L. So this becomes AZ for a short dipole is just equal to mu 0 over 4 pi times I naught. Now, here we're assuming I naught's the same everywhere. That's not quite true with any short dipole, but it's good enough for what we're talking about here. Then we're going to take that, it's got to be times the length, right? It's got to be weighed by the length of the wire. The longer the wire, the more A we have out here. But we're still assuming it's much less than a wavelength. Then it's going to be times e to the minus j beta r. And this would be in the AZ direction if I wanted to make it a vector. Do y'all agree with that, class? You can look in the book, that's what he has. And I did this last time. Now I made the claim that in the far field, if you have AZ for a short wire antenna, and I'm assuming the short wire antenna is in the direction Z. If it's not, if it's in the X direction, you've got to make this AX. And this angle loses its meaning in a general sense, but it's going to be an angle that will be, it will be the analog to theta if Z is in the vertical direction. I'll get to that in a second, okay? So let's go ahead and get the E field from this. Well, I said E in the far field for a short dipole. Let's look at this. It's equal to minus j omega times A to Z. That's AZ. So it's times mu 0 over 4 pi times L, right? And then it's going to be e to the minus j beta times I naught, sorry, R in here, and it's going to be, and now it's going to be weighed by sine theta in the A theta direction. Just look what I put here. That's A theta. There's AZ. I just copied AZ from here to here. That's my AZ, isn't it? For a short dipole, you all see what I'm doing? Now, actually, let me do one thing here. I'm going to try to explain this here. You see how AZ is in that direction, right? And you see I put a minus on it. Just watch it. When I get the component in the theta direction of this, this is A theta, isn't it? You know, if you think about the arch angle here, theta measured from here to here, A theta is in that direction. Y'all with me? I'm going to have to adjust this in a second. Well, when you take the projection of this onto A theta, what you're really doing is taking the projection of this vector on that axis right there, if you can imagine this. You okay with this, class? And you have to put a minus sign because A theta goes that way. I'm going to say one thing. Just make this plus. I'm not going to make this plus. It will be plus. And that's the actual E field. Now this is going to be, I better make this plus. Well, let me do this. I'll leave that negative and I'll try to explain this a little more later. But here's what I'm really getting at. The E field, the propagating E field from a short dipole, if it's in the Z direction, will have only a theta component. This is the far field. You can get it by taking the value of AZ, multiplying it by j omega, and multiplying it by sine theta. Are you with me? Now, why is that so good? Because you guys did a curl, some of you, didn't you? Curls are troublesome, especially when you're using something that's a non-conventional system, like you're used to spherical, Cartesian coordinates, and cylindrical, right? If you did the curl in cylindrical, then you had to do that whole 9 yards of that, and you had to turn it into something that could be rendered in spherical, right? If you wanted to get the correct E in spherical, right? And you found it just had an E theta component. No matter how you do it, it's a problem. But when you get proloid spheroidal coordinates or something like that, that are not standard, but they're very useful, then the curl's a nightmare. Okay, you hear me? But this is easy, and this is sort of a thing in graduate school when you're working horrific problems you appreciate. Because all I need is A in the far field, and then I just get the projection of A in a direction perpendicular to R, which is theta, all right? It's going to be that. And then I weigh it by the sine of theta, where that angle theta has to do with the direction of the current and the angle of the vector R. That's the only thing you need. And you'll see this becomes more useful. Now, what's the E field in the book for a short dipole? Do you remember? What was it? It was J, take a look, beta, well, actually, the way Wentworth's book is, he has this equal to J, eta, beta, L, I naught, look in your book, over 4 pi, right? Then it's going to have e to the minus j beta r, right? And it's going to be times the sine of theta, a theta in the far field. Do you have your books, anybody? Anybody have a book they can open up? Go ahead and take a look and find it. I forgot the actual place it is. It's be under the short dipole section. And I'm going to show you how that is equivalent to what I wrote above. It'll be E. I mean, he might have H, but H just multiplied by 80 and you have E. Pretty sure you have E. I'll start. That's efficiency. That's radiated pound. Oops. Holy cats. It look it back. As colorful as anything I've ever seen. It's called a Hertzian dipole. It's on page 443, equation 850. He's got the beta at the end, but I always break J, eta beta out in front. You're going to see why in a second. Y'all see it? Do you have your book in a PDF format? Or if you look, can you see equation 850? Is that right?
Yes.
All right, now here's the deal. Circle this. Right here, eta beta. I want to show you something. You notice how I have omega mu naught? Mu naught's one constant. Omega, I know, is 2 pi f, right? You're not going to have to remember this, but this is nice. Let's talk about eta beta. Eta times beta. Well, what's eta in terms for free space of mu and epsilon? Does anybody remember? In free space.
Square root of mu over epsilon.
That's right. So that's the square root of mu over epsilon. It would be mu naught over epsilon if it was free space, right? The reason he might use eta there is because we know it's 120 pi. Then, what's beta? Well, beta is what? It's omega square root of mu epsilon, isn't it? In free space? For lossless? How many remember that? Try to jog your memory. Make sure you do at least feel the familiarity of this, and if you don't, put a question mark when I say something like this, because this should be something obvious. Now, what do you notice about this? I got square root of epsilon here, square root of epsilon here, don't I? Can you all see that? You know, the people with iPads and stuff, if you have good writing, see me after class, because I will post your notes. I have people asking about notes in my other class. Can you all read this, by the way, on it when he's got the camera or not? I'd appreciate it for me. If you can you send me your notes, either one of you two? Just send me the notes and I'll post them so everybody can benefit, and I appreciate it. All right, now take a look at this. So I get mu, don't I? And then epsilon cancels. So I get mu epsilon. That is that. They're identical, in other words. And that's a lot easier to work with in the far field. Okay, that was my whole point. And I don't need to do a curl. That's another thing for far field. No curls. My life is better already. Curls used to irritate me to no end. Curls with Bessel functions and stuff like this can take hours. But now, here's a little tip. I wish I knew this when I was with you, right? How many know what Mathematica is? Well, Mathematica and MATLAB, but Mathematica is much better at this because it puts it in formats you just cut and paste and put it in. It'll do the curl symbolically. It'll do an integration symbolically. It'll give you the closed form solution, and the solution's in a form where you can cut and paste it, put it into a Word document if you're writing a paper or a journal article, or get it into what's called a LaTeX format. Does anybody know what LaTeX is here? LaTeX is probably the single thing scientists use all the time to write their journal papers, or mathematicians, or any technical person. Now here's another thing for your benefit. Managers, people that let contracts go, use Word almost extensively. Scientists use LaTeX. It's much, much better, and you'll just find that. How many know that, or at least have the appreciation of LaTeX? One person, two, three. You will find LaTeX is a godsend when it comes to stuff. It really is. And I was the first to complain about it, but I learned since. So anyway, that's my point. That's the short dipole, that's the electric field. If I wanted the E or the H field from this, how would I get it anyway? What I'd do is take E and divide it by eta, right? Correct, class? So really what I would do, if I divide that by eta, just there's one more step. I would get rid of this, and this becomes H. I'm not quite done though. There's one other thing I need to do. Anybody? The E field was in the theta direction, right? It's propagating in the R direction, radially away, right? That means E cross H has to be in the direction of propagation. If you remember, theta crossed phi is R. If you don't worry about it. But in other words, this will become phi. Now, if you look in your books, it's probably 49, 849, but you're going to see that formula for H, for far field. Do you see it? Guys, just write that. And that's how you get it if it's propagating. By the way, we're going to just deal with propagating fields. We're not going to, the near field itself is a little bit more complicated than we have time for. It's actually a lot more complicated. Near field is something, if you're working for a power company, or if you're doing work on the surface of like a military vessel or something, then you have to worry about near field values. I just talked to a friend of mine, Paul Ride, down in Pensacola. He's doing work for the Navy and has a large towed array that's going to be driven with about 100,000 volts. It's a long story. It's an antenna, low frequency antenna, and he wanted to know how to get the best way to estimate the E fields near the ground. That's near field. And I told him he's got a nightmare. He needs the exact description of the kind of wire that's tethered to it. And then what he has to do is actually get a numerical program to analyze that, because it becomes very tricky. Depends on the current, but primarily the voltage difference is going to do it, because there's lethal limits for human beings to be exposed to. And so that's the problem he's been. I taught him this class, this very class, yeah.
In this book, I could be dismissing it. It seems that there's an R function.
Oh gosh, yes. Sorry, I don't know how I neglected. It's 1 over R dependence. I'm so sorry. It has to be 1 over R. Thank you so much. Okay. I don't know how I forgot that. It's always proportional to 1 over R, E field and H. Now that should be the same thing you see in your book, isn't it? For H, right? But Wentworth's book leaves it in terms of beta. If you divide this by eta, you can just put 120 pi here, but mu 0 is 4 pi times 10 to the minus 7. Eta is 120 pi, right? So 4 over 12 would be 30 pi. You can make adjustments. I'm just showing you some of the things I consider. Now that's the electric field and H field from a short dipole. I'm going to worry about a short dipole. We're not done yet. We need to find the total power radiated. That's next, and this is in the chapter. So how would you find the total power radiated? We call it P radiated. Anybody? Well, how about we find the average power density first? And this is for a radiated electric field. What's if we've got a wave that's propagating? How do you find the power density? Well, what's the fundamental way? Right, that 1/2 the real part in the phasor domain of E crossed H conjugated, right? That's formal. If you wanted to do the whole 9 yards, you do this. You have E and H. You could cross them. You can get it. But we're a little better than that. We know something as a group. We know it's really just equal to either 1/2 times the magnitude of the E field. This is for propagational. Squared divided by eta naught, and it would be in the AR direction, right? Or it's also equal to 1/2 times the magnitude, or times eta, right? A to naught in this case, times the magnitude of the H field squared in the AR direction. Now you notice I put how come I can do this, by the way, anybody? Well, think about, what is E in terms of H? E is eta times H, isn't it? So if you put eta times H and square it, you get eta squared, H squared. There's an eta downstairs, you just get a single eta. That's how you get that, right? So in the for propagating fields, either one of these two gets you the magnitude of the power density. For R's, what is it going to be? Let's use the H field. Here's the H field, right? Help me out, guys. What happens when I square that? What do I get? Let me make it even simpler. Y'all follow me on what I'm up to? I need the square of that to stick in that equation, right? So if I get H squared, how am I going to do this? Well, first, before I square it, here's what I do in magnitude. Beta is actually equal to, it depends how you want to do it. Isn't it 2 pi over lambda? How many know that? Beta is 2 pi over lambda, isn't it? Right? Because lambda times beta is 2 pi. So I can, if I want, just put 2 pi over lambda. Now you can see one thing I'm about to do next. What am I about to do next, Tyler? Jack? There's no wrong answer.
Cancel the pi's on the numerator and denominator.
Yeah, that's, for starters, there's one other thing. Jake? What am I going to do?
Make it over 2.
How about the 2 and the 4 go to 1/2? With me? And how about dropping the lambda downstairs? So now, and the L. So now what I'm going to do is this. I'm even going to get rid of that J for now. So now I have J here, and then I have what? I have 2, don't I? Right? And I have lambda here, right? Correct? Isn't that it? Take a look at what I did. Wouldn't that be the same? You with me, Tom? What did I have there before? I had A to beta, right? Beta is 2 pi over lambda, right? Here, tell you what, let's do this. I mean, not eta, I just had beta, right? And then I had, actually there's an L in here. I somehow got rid of it. It's L over 2 lambda. Agreed, class? Just check in. You're with me? I'm trying to save a little space. And the people that take notes, just put your hand up if you want me to slow down. Because I'm notorious for moving too fast if I'm not careful. Now I got that. I want to square it. I want to take the magnitude and square it, right? So when I take the magnitude, don't I get rid of this? If I just take the magnitude. Now what about this? The e to the minus j beta r. Isn't that really e to the j some angle? Right? Isn't that always 1, the magnitude class? How many know that? Right? The magnitude of e to the j beta anything, or e to the j any angle, is always 1. So I can get rid of this too. Okay, now I got it down to the point I can do something meaningful. That's overall. Now I need to square it, don't I? With me? Everybody? Nathaniel, can you see it back there? You guys in the back row, you guys good? I always worry about this. So when I square it, what do I get? My magnitude of 8 squared becomes, really, I'm going to take the 2 out, or the 2 squared out in front becomes 1/4. Then we have L over lambda squared, I naught squared, over R squared, times sine squared of theta, right? I want the power density here, right? Just listen to me. So I'm going to multiply that by 1/2 first. Y'all see what I'm doing? When I multiply it by 1/2, I get an 8 down here. I hope I'm not going too fast, right? This is the thing you need to take. I'm not done yet. That's the 1/2. Now, when I multiply by 8 and naught, listen to me, that's 120 pi, isn't it? I'm just going to leave it in free. So now I multiply this by 120 pi. Now it's 8 and naught. And that's the power density. You all see how I'm probably going to even streamline that. How about Nathaniel? Well, how am I going to, can you see that 120 pi on top?
Yeah.
What am I going to do this 120 pi over 8 to make it easier? Isn't that 60 over 4 or 30 over 2, or 15. How many see that? Pi. So, and guys that are taking notes, I don't want to erase this and leave you hanging. But I'm trying to do this to show you how I think about this. So I try to reduce it in complexity. I'm just going to put 15 pi here if you don't mind. Okay? So that's just, and again, this is for free space, pi. But now I have what? I have p average, right? Agreed? Don't, please, if you feel this is too much, it's not. It's easy. What I'm showing you is how you go about thinking about calculating the total radiated power from any antenna. This is how I do it. I simplify the equation, so mathematically I got the minimum number of things I worry about. I can go a step further. I can just make that a constant. All right, I could make the 15 pi squared L over lambda squared I naught squared all a constant. Then I have 1 over r squared. Matter of fact, let's do this. Because this, like when I was, they didn't have really fancy computers that could solve all sorts of stuff. So we did all sorts of things empirically. We did all sorts of approximations to do the integrations and stuff. But you all see, and we also did this. This is a shorthanded trick. That right there we'll just call K. Matter of fact, let me include the I naught I squared between there too. So I'm going to just call this K. That's got an I squared in there. All right, and if that's K, now I'm going to go over there and do the integration. One time I'm going to show you this, okay? We're going to calculate total radiated power. So now I come over here and I say my average power density. You don't need to write this, but I found it. It's equal to K, right? Then it's going to be times the sine squared of theta over r squared, and it is in the AR direction. And that would be in watts per meter squared. K is, of course, the thing I circled in blue. You good, everyone? Nathaniel, can you see? If you need to, just come move over here.
Yeah.
Because you're stretching your neck, and I know that.
No, I'm just.
You're looking through his head, I know.
I think in the direction AR.
Pardon? AR? It's got to be in the radial direction because actually if we do E cross theta, E is theta, H is phi, so it's got to be an R. And any propagating field always is moving directly away from the source. The source here, I'm assuming at the origin, oriented in the z-axis. I come down to that, now I got to find the total power radiated. So how do I find total power radiated? I'm going to put it right here. P radiated. I like to do this one time. Well, it's going to be a surface integral. It's got to be, put an imaginary spherical surface around the antenna at a distance r away. Everything going through that is radiating away. Do you agree with that? So first I'm going to put this down so I know it's going to be K times sine squared theta over r squared. And that's my average power density. It's in the AR direction. Now I've got to dot it with a surface element. And if you remember in spherical coordinates, if I'm out at distance r and I want a differential surface of that, I have to take what? I have to take RD theta, wiper arm that's going in the theta direction. Then I have to take R sine theta d phi, wiper arm going in the phi direction. Do y'all remember that? When you do the two and it comes down to, it's going to be R squared sine of theta, right here, times d theta and d phi. Here's a question for somebody. So, do y'all remember that? Back in the day when you did integrals over a surface of a sphere, right? If you're wondering what surface it is, it's this surface. If you have a sphere of radius r, right? And I look at the differential surface here, this wiper arm distance would be r times the capital R sine of theta d phi. This wiper arm distance vertically down would simply be r d theta. And those are the edges of that little differential square that they put on the surface. Remember, r is held constant. So that's how I get this r squared sine theta d phi. Now, somebody, how about, see, I'm trying to think how to pronounce it. What does the theta go from where to where? Think about theta. Straight up to straight down would be the r vector. Straight up, theta would be 0. Straight down, theta would be pi. 0 to pi. Remember that. So theta here goes from 0 to pi. All right? People get a little nervous when I start asking. If you don't want to do it, just shake your head. All right, so how do I get phi? What's phi go from? What's your first name?
Harry.
Harry?
Harry.
Harry. How do I get the phi? Where's limits on phi? Take the horizontal plane. Go on the x-axis. That's 0, right? Phi goes from 0 all the way around or
2 pi.
or 360 degrees, right? Either one, 2 pi. I try to make sure you at least visualize this. Now, next. Is it Lydia? I messed you.
Yeah.
I know what your last name's like. Ganesh or something like that. Anyway, what is it, Lydia?
Yes, sir.
All right, now, what can I do to help myself here? Take a good look. I hope you can read my writing. Anything you notice, and this would be in the AR direction. I didn't put that down, but the differential surface is in the air. So what can I do with AR dot AR? Anybody? I'll ask you. What's the dot product of AX dot AX? 1, right? What's the dot product of AX dot AY? 0, right? The dot product is magnitude of the first vector, magnitude of the second, times what? Times the sine of the, or the cosine of the angle between them, right? If they're aligned, the cosine of the angle is 0. So AX dot AX is a value of 1. Magnitude of 1 is 1. AX dot AY, angle is 90 degrees, is 0, is it? Right? How many remember dot products? Didn't you have dot products when you did this? How many had dot products, whether you remember them or not? Okay, thank God you have them. You'll be exposed to them. So anyway, the AR dot AR goes to 1. Forget about it, right? What? Anything else, Lydia, that you're suspicious about you can get rid of? Besides me. Go ahead.
The R squared.
Yeah, the R squareds. Thank you. Whoever said. Nathaniel, was that you?
Yeah.
All right, R squareds, right? Get rid of them. There's no wrong answer. So, if you actually saw the proofs that I used to do, because they were massively long, I would have all sorts of crosses and stuff like that. So now I have sine theta times sine squared of theta times k, right? Now, if you I know your calculators whips this out in a heartbeat, but what might I do with those two things to do the integral? And you don't need to write this down, but you can just go along with the game. And not you can. What would I do with sine squared to make this a feasible integral if there was money involved? Say $100,000. Then people think real well. Guaranteed for $100,000, I'd have everybody in here get the right answer in about 1 minute, because they have Google.
Would you do the trig out of it?
Sure. How about 1 minus cosine squared? Agreed? Stay with me now. Hope you don't mind this kind of lecture, but it's important right here. So I'm going to take 1 minus cosine squared of theta. Now, obviously, at this point, you're starting to see things a little clearer, right? Now, what do I do? From the whole class, anybody can share. How about you, William? I haven't picked on you yet.
Could you factor? I guess you can't factor out k though.
Well, sure you can take that. It's constant. Right?
Yeah.
Get rid of that. That's actually not a bad way to do it. Get rid of everything you don't need inside the kernel of integration. There's one overwhelming. Yeah, go ahead.
Make u equal to cosine of
Yeah, why not make u equal to cosine of theta, and then du equals what? Minus sine theta d theta, right? Y'all remember doing that crap? Student, that stuff? Y'all remember that, right? I remember doing these things. Sines, cosines, okay, when they get Bessel functions, I don't know the antiderivative of a lot of higher order Bessels. It used to drive me nuts because the physicists know this stuff. Oh, it's obvious. It's not to me, is it? And you probably feel somewhat that way about what I'm saying now because you haven't done this in a while. All right, so now what I'm going to do, if this, remember the integral limits. Now think about this. The phi integration still goes from 0 to 2 pi, right? But now, since we're making the substitution of cosine theta, just listen to me, then cosine squared is u squared, right? One time I want to do this. Can you see in the back? All right. u squared. All right, what is sine theta d theta? It's minus du, right? With me? So that becomes minus du. I'll put the minus sign here. So it's du. Now, we're going to do this integration. If you all understand where I got everything from, let me circle that minus sign. That's a habit I got into early, and I always make French 7s like this when I do work, because if I make regular, I think it's a 1 a lot of times, because I'm sloppy. That's me. Sometimes I think it's a 2 if I'm writing fast like this. If I don't do that, I'll mess that up, so I always make French 7s. All right, now, how am I going to do this integral? Just listen to me now. When I put people on the spot, I know what it's like. It's like, I look like an idiot. Don't worry about that. Well, if you're going to do this integral, always start with the easiest part. d phi integrated is just phi, right? Phi evaluated from 0 to 2 pi is 2 pi, right? Might as well get rid of that minus k. So I'm going to have minus 2 pi k right here. And now, miraculously, I got rid of a lot of that integration stuff that was there. Now I got to focus on this one. Not quite done yet. What do I need to do with these limits? Well, I got u there, right? Those are for phi. So now I got to go here and I say, well, if theta right here is 0, what's the cosine of 0? 1. And what is the cosine of pi? Now here's my next trick. Some of you know what I'm up to. That's minus 1. And I got one other thing to say now. Now just think. Well, what happens if I change these limits? I put minus 1 down here, 1 here. What do I do to this anyway? Put in negative side. Remember, if you go from integral from a to b, and you flip the limits, you go from b to a, just minus that, right? So that's what I do. I make that minus and that plus, and now I throw a minus sign there, which makes this plus. With me? All right? Actually, I'm going to just do it. Now it's equated. Now, keep going on. I got to take this, and I do this integration. If I integrate du, I get u, right? U from 1 minus a minus 1 is 2, isn't it? Right. All right, so it's 2 right here. That's the first integration. Then it's minus what? Integral of u squared du is 1/3 u cubed, right? Or u cubed over 3, right? So many people might start despising me. I'm trying to do this for a very important reason. If you see the thought process, it'll help you a long way in some of the stuff we're going to do. All right, so that's going to be u cubed over 3, evaluated from minus 1 to 1, right? Okay, let me just finish it up. So what's that going to be? That's going to be 2 pi k, right? And now I've got 2 minus 1/3. U cubed is 1 minus, now I've got minus 1 cubed, right? Well, what's minus 1 cubed? Minus 1 times minus 1 is 1 times minus 1 is minus 1, right? So it's minus a minus 1. Hey, look, I'm doing my best. So what happens here? I really have 1 minus a minus 1 or 2. So I'm just going to make that 2/3. All right, we're almost done. You look at me, my God, thank God. What's 2/3 minus, what's 2 over minus 2/3? Isn't 2 really 6/3? 6/3 minus 2/3 is 4/3, right? Just leave it as 4/3. And now you can see I have 2 pi times 4/3, or really I have 8 pi, right, over 3 times k as the total power radiated. I'm almost there. Remember, we put k down here, didn't we, class? I'm erasing k, but y'all remember when I circled with blue? Okay, so then you find the total power radiated by going ahead and putting K in there, right? K was I squared, right? It had L over lambda squared, right? And it had 1 over 8 pi, didn't it? If you look in your notes.
15 times.
Or 50, sorry. It had 15 pi's. Sorry, we did that, forgot the 8. We did the 8s substitution. So when you do the whole 9 yards and stick in that, you find the total power radiated. And I want it in terms of the things I'm putting in here. Look in your book. You're going to see this total power radiated is going to be 40 pi squared, I naught squared, right? And then it's going to be L over lambda squared. Take a look just for a second. And I don't know where that is in your books, but you've got, you got your color coded book. I feel better with that. What is it? Equation or page 444? Yeah, there it is. If you look on 8.55, you're going to see what I came up with. Now, I stuck the K in my head and put it up there. You can do this, but this is how I do business. Now, that's the whole 9 yards of how to do. Find the total power radiated from any antenna. Find the E field from the antenna or the H field. Get the power density, then integrate the power density over a surface. R squared always cancels. Remember that. And you get it. So I've got, this is the total power radiated. Now, here's an important point. Yep.
So it's 80.
Huh?
It's
So that's
80.
for the resistance radiated.
This 80 pi is resistance. Let's look at total power. Look at equation 855, is it? Right there? Right, that's, you see it? Now, I'm about to get to what he just got to, and that is the radiation resistance, and this is the single most important thing. Then we're going to get the gain. I'm going to get it done, I hope. I love doing it this way because it saves so many questions. I'm asking your questions and trying to answer. And you usually do a real good job. And sometimes, especially if kids are like in a mode where they just got out of the test and they're kind of high strung, they're really chatty right here. So now I've got that as radiated power density. Well, what is power in general if you have a resistor and you got a sine wave driving? Isn't it what? There's always a 1/2 V squared, right? Divided by R. Isn't that right for if V is the RMS, or the average value? Not RMS, if V is the peak value. Or it's 1/2 I squared R. How many remember that from circuits, right? That 1/2 is because we're talking about peak values of the voltage or current. Well, this is also equal to 1/2, and then it's going to be R, call this the radiation resistance, times I squared. Now, that is called radiation resistance. It's very important. It's in ohms, of course. What that is something where it gives you, if you know the current feeding at an antenna, the radiation resistance has to do with the amount of power that's launched. And this is interesting. So we're taking power into an antenna that's in terms of a current voltage. And instead of heat, even though we could heat it up, we're launching electromagnetic energy. So the antenna is itself a transducer. It takes current voltage, turns it into electromagnetic fields that propagate, and the actual corpuscles, the smallest part of an electric field, is called a photon, believe it or not. You might have heard of that. So what you get is these, they call them ensembles. A huge number of photons are being launched. By the way, photons have momentum, which is very interesting. So here you've got something that's launching stuff, and it's got zero momentum on that device, but because it's launching photons in every direction, the same way, there's the net momentum change on the antenna is zero. Now with focused antennas, you actually get a small but measurable force from the amount of power you project. It's extremely small, but at least should be noted in case you're doing deep space stuff. And the reason I mention this is a lot of physicists overlook the obvious. We had a communication satellite tumble to Earth and hit Australia, and back in the 60s it was called Telstar. And the reason it came down is these physicists that did all this work, strangely enough, they didn't have a lot of engineers on this one, I guess, from what I read. They looked at the effects of atmospheric drag. They looked at all the obvious things, because obviously if you got something in an orbit, there's some friction just on the very, very thin atmosphere that's up there, right? There's always something. And that slows it down. And it kept decaying and decaying much faster than they thought. It crashed. And they were beside themselves. The thing they didn't figure out was there's also, whenever you have things moving at a high velocity, like a satellite, and you're cutting magnetic field lines, you generate a charge separation or a voltage on the satellite. And that voltage arcs in the plasma. And that causes a huge amount of power dissipation. So I'm throwing this out there as something that shows what else you need to consider at times. I'm telling you this because I would want to know this kind of stuff. So this radiation resistance in itself talks about an important concept, how the antenna translates electric voltage and current into radiated power, okay? Just like a hairdryer does, only now we're not talking about infrared photons, we're talking about much lower frequency photons that are launched. And they're actually in terms of an electric field because a whole bunch of them assemble together and they actually create an electric field. Now, that's a little beyond scope, but at least you got appreciation. Now, here's the deal. That's the thing you want for all antennas. That and the gain. Last thing I'm going to talk about, you all with me on that? That's how you get the radiation resistance for any antenna. Loop antenna, half-wave dipole, aperture antenna. You find the current distribution. Then you calculate the electric field or H field in the far field, and then you find the total power radiated. This is the way it's always done. So now, if you have that, you can see something else. The radiation resistance is equal to this. This would be I naught. And you can see that the I naughts cancel. And when I multiply by a factor of 2, I get 80. And now you say for a short dipole, and again, I tend to do this, that means the length of the dipole is less than or equal to lambda over 10. We find the radiation resistance, R, I'm just going to call it R rad. Radiation resistance is going to be 80 pi squared L over lambda squared. Now this is an important point. We know that L has to be a tenth of a wavelength, right? Just listen to me now. So if we talk about the maximum resistance of a short dipole, if you make L a tenth of lambda, you would get 1/10 here, correct? Are you with me? Just listen to me. So if I go ahead and I say R rad here, and you can put down max, now I'm going to get 80 pi squared, which I don't care for, because I don't know that one by heart, 80 pi squared, and then I'm going to get 1/10 squared. Well, 10 squared is 100, so that means I get 0.8 pi squared, right? And this would be the maximum radiation resistance. Now just look at that for a second. What is that value? What is pi squared? Isn't pi about 3 if we're going to just ballpark it, guys? 3.1415. So if you take pi and square, you get about 9, right? Call it 10. 10 times 0.8 is 8 ohms. So this is of the order of 8 ohms max. That's horrific. You would like a radiation resistance to be up, because that means it takes less current to send that much power. Do you all follow me on that? Assume your current is constant. The greater the radiation resistance, the greater the power transmitted. They like low current antennas for one reason. You don't have ohmic losses that heat the wire and cause a lot of power loss. You like very high impedance antennas. This is something you can do adapters. You can do things that actually, like transformers, would take a low impedance, make it a high impedance. But the problem is, when you have a low impedance antenna, at that point, once you get current on the antenna, it's still heating up the copper, and it's going to thermally heat it, and there'll be a power loss there. So you would like a very high input resistance. Got me on that? That's beneficial. Now these short dipoles are really just useful to go through the proof. The next thing I'm going to talk about, and I'm about out of time, but here's what I'm going to do, is ask you in your books, if you turn with, yeah, go ahead.
All these equations we threw out today are only for the Hertzian dipole.
The short dipole, but what I was about to do, and I didn't get to it, the gain for this antenna, how would you get gain, by the way? Let me just finish this thought, okay? If you have to go, you go. And I know you got a job, but if you wanted the gain, what do you always get if you want gain? Or the directivity, let's assume the efficiency is 1. Well, when you want directivity max, right, it's just equal to 4 pi over that crazy integral of the normalized power density as a function of phi and theta times the sine of theta d theta d phi. I know you guys probably are looking at this as, I don't know that by heart. You'll get used to it over time. You really will. We know the integration here is over the spherical surface, so theta goes from 0 to pi. Phi goes from 0 to 2 pi. If you listen to me, I'm going to make it real simple because I'm out of time. How many understand at least where I got this from before? Now, Nathaniel, can you see it?
Yeah.
Now here's the deal. That normalized power density, you remember the E field's a function of sine theta? Just sine theta? Take a look, right? Remember that was I got that from AZ, right? Because of that, when you square it, the normalized power density. You can forget about I naught eta. The sine squared will be the normalized power density here because that's the only function of angle. Do you follow me? These normalized power densities, you throw out R, throw out I, throw out eta. The only thing you take is the E field squared and take a look at what the angular function is. If the function has a max value of 1 and the sine does, just take the angular function, put it in there for the normalized power. But what do you notice happening? Isn't that going to be a sine cubed integral? As we had before, it isn't sine cubed really 1 minus cosine squared times sine theta? And didn't we just do this and circle this? This whole 9 yards here, all right, simply becomes 8 pi over 3. I know that because I do this stuff. And that means D max for a short dipole becomes just 3/2, or 1.5. And the directivity in general will be 1.5 times sine squared of theta. Let me show you where all this stuff is sort of brought down in catalog for everybody's best interest, so you don't go nuts trying to redo this every time. But if you look on page 466 in your book, you have a text. If you don't, just write down 466, and you're going to see parameter, magnetic field, time on the vertical axis, symbol, and then they have the antennas. We did the Hertzian dipole. You see that? It goes down there and it shows you what the actual time average power density is. I actually calculated that. The maximum power density. It shows you the normalized power density is the next one. The solid angle is really the integral of that lower part of the directivity formula. It shows you the maximum directivity, and it gives it all the things. The short dipole, the small loop, all have the same. Now the half-wave dipole have the, I hope you got something out of this lecture. I want to make sure you saw the reasoning. I'm going to give you some homework. Good question. Friday, are we having a quiz? Yeah, we'll have a quiz, and you know what's going to be on? Look at her. No, Dr. Ginsey, not a. It'll be on this lecture's homework and the prior lecture's homework. So it's going to be related to directivity, related to power density. In other words, because you're going to want to know exactly what you're going to do. If I'll give you any hard stuff, but I'll give you some homework that are going to be representative of the quiz problem. Fair enough? The last quiz was easy. And don't shake your head. It's not that painful. It's not going to be bad. I mean, I can only tell you, the last quiz bad, guys? Thank God somebody said it was. If I suck bad, then I'm really going to feel, I'm like a